So we've covered an example of how to do related rates, but now we're going to do one that's a little more challenging. So we have this algorithm here, and let's see if we can't use this algorithm with this problem. So what I've got is I've got a trough, and it's 7 feet long, and it's 2 feet across the top, and these form an isosceles triangle with altitudes of 2 feet. So I've got some sort of spigot or faucet or whatever, and it's pouring water in at 1 cubic feet per minute. Okay? And then I want to figure out how fast the water is rising when the height is 0.5 feet. So what I have to do is I have to figure out how to solve this problem. So I need a little bit of modeling, a little bit of how to construct this problem. And this is going to be a little challenging. So what we're going to do is what we want to think about is we want to think about the fact of, okay, I know that if the water is going in at 1 cubic foot per minute, that it can't just be the same, the height can't be changing all the time, because by the time I get up here, all that water has to spread along that big flat plane. But down here, a little bit of water makes it rise quickly. So I know that it has to be some sort of change. But the first things first, how do I write an equation of the relationship being described? This particular problem, this is the hardest piece. And in most related rates problem, this is the hardest piece. So in these types of problems, what you want to do is you want to take the general equation. This is the whole trough, but what about this little trough? What about just the blue water part? Well, what I notice when I do this is that I end up with a prism. Right? It's not drawn super great, but the idea is no matter how high the water is here, no matter what the height is, this triangle is similar to the larger triangle, right? It's going to have height. It's going to have an altitude of h, and it's going to have a base width of h. And it's always similar to the 2-2 case, right? But I also noticed something interesting, that no matter how tall this is, it always has a length of 7, no matter what. So if it's h, h, and 7, excuse me, I'm very sorry for that. So if it's h, h, and 7, I know that I can construct a volume using that prism. So if you remember anything about the volume of a prism, the volume of a prism is the area of the base times the length, right? Because you're going to take the area of the base and you're going to kind of stretch it by that length. So what I need to do is I need to find the area of a triangle with base h and height h. Well, I know that. So I know that v is 1/2 h squared. And I know that length is always 7. So it's 7/2 h squared. So then at this point, I have a volume. So notice that in the case where h was 2, like we're all the way up, that you're going to have a volume of 14 cubic feet, roughly, which is about what you'd expect. 1/2 times 2 is 1, 2 times 7 is 14. Okay, so then once we're done with that, we need to differentiate. Well, this is with respect to time, right? It's 1 cubic foot per minute. So I need to take the derivative with respect to time. Now, in this particular case, that's simple enough. That's just dv dt. Now, if this was the derivative with respect to h, right, don't worry about this t. If this was just with respect to h, I would end up with 7h by the power rule. But because I have that extra piece, I end up with dh dt. Now, I have this piece, so this part's done. I have to plug in the known information. Now, I'm trying to solve for this because it's asking me how fast is the water rising. Well, that's the derivative of the height, right? That's the rate of change of the height. But I have this. So 1 cubic foot per minute. Well, cubic foot is a volume. So that tells me that the volume with respect to time is at 1 foot per minute. And then I also have this. So this tells me about my current state at h. So that tells me I can plug in this. I can plug in this. So that tells me that dh dt is equal to 2/7 foot, per minute. Now, if we really wanted to be careful here, we would do this as feet cubed per minute. And since this is, and it was 7 feet, so this is actually 7 blah 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 feet, and so on and so on. Like, you can match the units, and that's good. You want to match units. But ultimately, it's 2/7 feet per minute is how quickly it's changing when the height is half a foot.